So we already have the problems number 2. Okay, so the group, please go to the boards to write your names. Okay, and then we have 5 minutes for reporter. Okay.
没事。
can handle the problem.
Okay. Dear judges and fellow debaters, this is the order of the laboratory team, and today we are going to report problem number 2, droplet microscope. This is the outline of our report. Here is the problem statement. By looking through a single water droplet placed on a gas surface, one can observe that the droplet acts as an imaging system, investigating the magnification and resolution of such things. So the main focus here is the magnification and resolution, while our parameter of discussion is the water volume and the ring diameter. Well, the ring will be discussed in our experiment later. Here is our observation video. As you can see, as we add the amount of volume of the water here, the imaging system will have a bigger magnification rate. This is our theory, the lens maker formula. We define that the R1 and R2 as the radius of curvature, and the NW and N alpha as the reflection index of water and air, and W as the thickness of the droplet. This is the lens maker formula. Well, since R2 is almost infinite, as this is a flat surface, we can rewrite the formula as this. So we can find the correlation between R1 and the focal distance. So we can calculate the radius of curvature. We assume that the droplet can be considered as a part of sphere. So we can calculate the volume and its correlation with the curvature right here. It's just integrate. So our parameters of discussion. The manipulated variable is the volume of water and the ring diameter. The response variable is the focal length of the droplet lens, the resolution of the droplet lens, the magnification of the lens, and the distortion of the lens. So, in our experiment 1, we want to find the focal length of the droplet lens. So, this is a schematic diagram of our box. This is a light source, this is a laser beam, and a transparent plate, which is just named as the glass plate that the problem statement has just talked about it earlier. And the droplet is right here with a ring diameter. So we make the droplet inside of the ring. And we can measure the focal distance. So we place a ring with different ring radiuses of 5, 3, and 2.5 millimeters on a transparent plane. And we drop some water in the ring to form the lens. So we turn on the monochromatic light and move the screen to the light spot is the smallest. Well, the reason we use monochromatic light is to ignore the dispersion in this phenomenon. Now we measure the distance between the transparent lens and screen, and we change the water volume and redo the experiment every time. So this is a graph of our experimental results. You can see as the water volume increases, the focal distance decreases. And this is a result of the R when it is at 3 milliliters. It is also a linear correlation. And this is when it is at 5 milliliters. But as you can see, when the R is smaller, the focal distance is bigger than when the R is much more little. So, in a small variation of water volume, the volume of the water and the focal distance can be regarded as a linear relationship. Due to the small variation of water, it is only a small part of the big picture. So we can state that this is a linear correlation. And B and F, meaning the volume of water and the focal distance, has a negative correlation that we can see in this graph. So in our experimental 2, we want to measure the resolution of the droplet lens, like how the problem statement has talked about. So we use radiate criterion to measure the resolution. Well, the light is passing through the circular aperture. It generates a diffraction pattern, which we call an airy disk. And through the radiate criterion, we can have this formula, which the theta is the minimum resolvable angle, and lambda is the wavelength, and d is the diameter of the lens aperture. So, when we are observing two objects, this is what we want to see. It is a radiate criterion, and it is just resolved at this point. So this is a schematic diagram of our box. we use this graph to check the resolution with Rayline criteria. And we use camera to record the entire process. So we, again, place a ring of these different millimeters on the transparent plane, and drop water in a ring to form the lens. Then we place lens 50 centimeters upon the graph paper like this. And we take a picture here to analyze it. And we change the water volume and redo the experiment. So our method is to calculate the theta here. Well, because the theta is very small, we can approximate to the minimum resolvable distance dividing the distance here. Well, this can be approximated because the theta is very small. And to reiterate, the distance here is the distance between the lens and the resolution. And here is our experimental results. You can see correlation right here. And this is the result of our experiment 2. And we can find that the theta squared is related to f. Although we have no theory, but our data matches with this correlation. And we will revise the experimental results by a magnification rate. So we can revise the actual minimum resolvable distance to the minimum resolvable distance of the image. And this is the result after the revise, and you can see that this is a linear line. And this is a linear line as well, and we will discuss the correlation later. And in our experiment 3, we want to discuss the magnification of the droplet lens. The magnification, and here are some of the height of the object, the height of the image, the object distance, the image distance, and the focal distance. Okay, so we define the magnification as this: the image and the object's distance and height. And so we apply the Gauss lens formula, and we calculate the image distance right here. So we put this into our formula, and we get this correlation, which has an intercept of 1, which we will be talking about in our data analysis. So this is a schematic diagram of our device. The camera is right here, and the droplet lens set is right here. And we will measure the droplet lens, and we will have droplet lens, a ring, and a graph paper. And we will measure the size of the image and the graph paper, and we will find a correlation. So we place the ring with these radiuses on the transparent plane, and we drop water in the ring to form the lens, and place the lens upon the graph paper to take a picture and analyze it. And we change the water volume and redo the experiment. So again, the size of this and the size of the graph paper is the magnification rate squared. So now we can know the magnification rate squared through this formula. And we can get a result. So when the R is equal to 2.5 millimeters, we can get a linear line right here. And you can see that the intercept is very close to 1, the same as our theory right here. And the slope is negative, which is also the same as our theory. And in 3 milliliters, it also matches with a theory with an intercept very close to 1, and the slope being negative. And with the 5 milliliter experiment, we can have the same correlation of close to 1 and a negative slope. So now we can conclude that m divided by 1 and f divided by 1 can be regarded as a linear relationship with an intercept close to 1. So in experiment 4, we now want to measure the distortion of the droplet lens. So this is a schematic diagram of our device. And we use camera again. So we place the ring, this time only 5 milliliters on the transparent plane. And we drop water in the ring to form the lens. We place the lens 30 centimeters above the graph paper this time, and take a picture to analyze it. So our method of measuring the distortion is subtracting the grid image distance with the calibrated grid distance, and we can get the distortion rate, which might sometimes be negative and sometimes be positive. So this is our experimental results. We can see that the distortion gets pretty big when the distance is more away from the central point. And for 460 milliliters, we can also see the rate of distortion, and it is bigger when it is away from the center point of the ball, of the sphere, of the droplet. And the 424 milliliters droplet, we can also see the same tendency. And this shows the same correlation as well. Well, this doesn't really have a very good correlation, but it proves my point. When the distance of the center point is bigger, the distortion rate is bigger. So there is no specific trend to the distortion because we cannot really get a formula from it. But at the edge of the lens, the distortion will go up to 25 to 30%, which is pretty big. So we can think that the water droplet is not necessarily a very good lens. So, in the conclusion, a small variation of water volume, the volume of water and the focal distance can be regarded as a linear relationship. And the big M, the magnification rate, divided by 1, and the focal distance divided by 1 can also be regarded as a linear relationship, and the intercept of 3 grams are close to 1. The angular resolution should be revised as the actual minimum resolvable distance here, and the lens to gram paper distance here, times by the magnification rate. And the droplet lens has a 20 to 35% distortion at the edge, meaning that it has a bigger, much higher resolution when it is close to the center point. Okay, this is the conclusion with our correlation and theory. Thank you.
Okay. So the corner.
Okay, so first, can I ask you a few questions about your setup? Do you have like for a common setup for all of the experiments? Like for example, did you say what you use to drop the water?
Well, in the article we use you can see it in the observation video.
And while you're looking for that, when you're at the observation video, I want to ask you another question. Is that why did you use the metal ring on the glass?
So to make sure that the R here stays the same.
So you keep on dropping the water until the radius is the same as the metal ring.
Well, yes.
Okay. And then can you explain what you use to drip the amount of water?
Well,
You use a plastic dropper?
no, it is a glass dropper.
Glass dropper. And so, okay. Then do you have any controlling method, like how much you press out of the glass dropper?
We look at the numbers of the milliliters.
Okay, so you use numbers. And can I ask you a question about the camera? What camera do you use? Phone or what?
I've been looking at my report because I think the camera has appeared many times.
Oh,
Yes,
okay.
this camera.
Okay,
It is actually pretty expensive.
Okay, then so you keep for the front part, do you keep the focal length? Like do you? Okay, maybe that's for another question. And then when you're doing all these experiments, do you close down the environmental light? For example, like flash lights,
Or no.
lights on the ceiling. Okay, then
Okay, time's up. So you have 3 minutes to prepare.
I'll be proposing the powder droplet microscope. So this is a problem statement, and the reporter stated that the main points they are focusing on the resolution and magnification and the water volume and the ring diameter. And their brief summary of the reporter is they use their observation and theory uses the lens maker formula and uses the Gauss lens formula as well. And they calculate the radius of curve and use the Rayleigh criterion to define the resolution and use other methods of determining the magnification. And their experiment method is placing rings on the transparent plate and drip the water with a glass droplet. And with the data analysis, they have a trend of no specific trend of distortion. And when the water volume increases, the focal will decrease. And the side of the water droplet will have the distortion rate of 25% or 30%. And the conclusion is that many of the relationships are linear when there is a little, when it is only focused on a small amount of change of volume. And the pros and cons of the reporter. The pros, they have clear demonstration of the phenomenon, organized results in data, they consider various variables, and have clear experimental setup and steps. But the cons, they didn't find a specific correlation between the factors and had no error bar and a lack of explanation of the data's correlation with their theory and lack of defining resolution. And has a lack of explaining of the whole conclusion page. And the point I want to discuss is for lens maker, because lens maker have is specifically used for one of the lens, and I want to also ask about their understanding of Gauss lens. And for the experiment method, I want to ask that do they think that environmental light will do some part of the experiment and explain how the I want them to ask for their how much they know about how this experiment actually works, and ask about the same volume of droplet shape will it vary the shape, and how to control the location of the drop, and do you think and what do you think will change when you change the water volume, and for the extension and others, and we want to ask that whether you think the droplet is thin or thick lens, and want you to elaborate more on the definition of resolution and talk about spherical abbreviation, which is a key point inside of this problem, and talk about how distortion and magnification affect each other. And now I want to invite the reporter. Okay. So first, I want to ask you a question about the Gauss lens. Can you draw like what Gauss lens looks like? Can you draw on the board, or do you have a picture? It's fine. If you cannot find the picture, you can draw it on the board.
And I said that the Gauss lens is actually the lens maker formula.
Oh, you said that they're the same.
It is actually the same formula.
Okay, so you said okay, they're the same. Okay, then can I ask you the question about lens maker? Because firstly, I want to ask you about like can I get to the observation video, please? Yes, for the observation video, we can. I see that you place it on the glass plate. Is it?
Yes.
Then. Yes. I see. Okay, so then do you think like the water droplet is a type of? Do you know thin lens or thick lens?
Well, this is a thick lens.
Thick lens, yes.
Because it is a sphere and
not all. Okay, then do you think this is able to use lens maker like
Well, we did use lens maker formula, and this is actually the thick lens formula here.
So
we made some assumptions about the curvature, and we have this formula right here.
Okay, and which I agree with you, which is the normal lens maker formula is not enough because of there's multiple layers. The refraction rate will be different, so the lens maker formula needs more multiplication, which I agree with you here. And second, I want to ask is that for using that camera, because I'm not really, because I don't know a lot about cameras, then can you? I want to ask a question about your camera. It's like, do you the front part? There's a big part where there's like many LEDs inside of the camera.
Yes.
Yes. Do you adjust the focal length of those things?
Well, the focal length of the camera can didn't change.
Did it change? So you control the focal length.
Yes. Well, if you use a phone to photo it, it will change. But we use a camera and we can change it by hand.
Okay. Which we think is free because with only using the same focal length that the magnification can be calculated correctly. And then I want to ask, can you turn to the definition of your resolution?
You mean the Rayleigh criterion?
Yeah, yes, Rayleigh criterion. Can I ask for can you explain what the D means in the Rayleigh criterion?
Well, the D is the diameter of the
Yes. Then what, like for example, in your experiment, what is the D? How do you measure the length of D in your experiment?
Well, we measure, well, this formula doesn't really have anything to do with our experiment. Our experiment is we use this graph to check the resolution. And we can find that in this place,
Yes.
the boundary, and this aligns with the Rayleigh criterion. And we can find the minimal resolvable distance right here.
Yes.
And we divide it by the distance, the length, and the resolution.
Yes.
And we can find the theta, which is approximate because the theta is small.
So you didn't use the one before, right?
Well, this is to explain.
You explain,
what
yes.
Rayleigh
And then
criterion
can I
is.
use the board? I want to show something. Is because for a normal microscope, I think there is another equation that maybe we have heard of. Is which I think this is very similar to your formula, which we think that these two have a correlation. But I want to say the difference is that this x, which is not just the aperture, it's actually the minimal defining distance, which I think is what your experiment is doing. So I think maybe using, like when you measure the length, I think you can use this formula, and you can use this x. So I think you can fit this formula, you can get the minimal best resolution that I can use in your theory.
Well, I think this is pretty much.
Yes. But you said that.
In our experiment, we don't need this theory to test out the resolution.
Then what do you use to fit your line for the graph?
We have several ways for.
Yes, but
You
the graph you use a fitting line, right? Then what do you use to fit? Like what function do you use to fit the line? Because you need a function, right?
You mean that for the comparison the result of the theory right here?
Yes. I think that for every line, I think there's you must have a theory to you know that it's linear, right?
Yes.
So I think shouldn't you have a formula like this to use the formula to know the relationship, because you cannot just fit randomly. Maybe it has some other kind of relation.
So we have a point. Yes.
Okay.
We did use these kinds of formulas to make a correlation right here.
Okay. Then I'll ask my next question. What do you think is the shape of the water droplet you drop on the metal plate?
Well,
The metal ring.
Well, we assume that it is a sphere.
The sphere.
But
Okay.
as the radius increases,
Yes, increases.
due to the gravity and surface tension and other forces inside of the sphere, it will not be appear as a sphere, and this might be the cause of the derivation in our experiment.
Okay. Then can I ask a question? Is that when you test the focal length, do you find out that the light cannot easily be on one spot? Because there is something called, like said here.
Aberration?
Yes, aberration. Like, can I know, shouldn't there be an error bar? Because spherical aberration, you say if it's a sphere, there should be error bar because it is arranged, not a dot.
Well, that is a valid point. Yes, we
Okay.
should have used error bar.
Okay, thank you. And then I want to ask a question on when you talk about magnification. Yes.
You mean this?
Yes. And I want to ask you the question that did you I know you use the camera to take the picture of the droplet inside of the droplet. Then I want to ask you a question that do you think that distortion would affect because you do the area, and if the distortion is positive, would it affect the M you use?
You mean the magnification?
Yes.
Well, we test the magnification in the center point of the sphere.
Yes. Then do you think that do you think there is, for example, when you talk about distortion, do you talk about the distortion of the center or the edge?
The edge we're talking about.
So you only talk about the distortion of the edge.
Yes.
Then do you think distortion will happen in the center of your?
Well, I do not think that distortion will happen in the center.
So do you
As
have?
it goes to the edge, the distortion rate will be significant.
Yes, yes, I agree with you on that. And then do you like have a picture of the magnified version of the like you had this of the experiment?
The picture.
Yeah, not just maybe okay. Or can you turn to the magnification, like where you have the grid and the normal grid and not the grid? Like when you have the grid on the side and the grid in the when you talk about magnification. Yes, this one. Like, do you think that there will be a minimal, like because you didn't take it from above, like top view, or is it with an angle?
The camera is vertical to
Vertical. Then do you think like there is aberration? For example, I can see that the middle part, like is kind of going denting inwards. Like the area, I can see that this is denting inwards. Do you think this is do you think this distortion will affect when you calculate the area?
So we only measure the area right here.
So you think, okay, so I think,
Well, this might cause some derivation.
so
but
you
I don't
think it's
that
very
it's
minimal, right?
Yes.
Okay, you think it's minimal, okay.
I mean,
Yes, okay. And then I want to ask you a question. Because you use, like you use a lot of different volume of the water, right?
yes.
Then, can I ask the question is that, what do you think the change of volume actually affects your experiment? Like, how does the water volume change?
Well, the volume will certainly affect the curvature of the sphere,
Curvature of the sphere.
and it will affect how gravitational forces function in the sphere,
Yes.
which will also change the curvature.
Yes, I agree with you on that. And can you turn to the page of, for example, focal length? Okay. Like you have. Yeah. Like for example, you have three different. You test different volume, right? You test different volume, right?
Yes.
Then what? Then can you explain like the downward part? Like why would this have a downward trend?
So we don't really.
Do you have theory to prove that downward trend?
Well, I think we.
Oh, then okay.
There is a downward trend, right?
Yes, downward trend. Then can you like draw? Maybe you can draw. You can if
Well,
you.
that is a phenomenon.
Okay, then, okay.
We really have a theory.
Okay, then next I want to ask you a question is that because lots of the experiment you said you only use it's linear trend because it is small volume, like there's small difference in
Yes,
volume.
because the volume is pretty small.
Yeah, then do you think that it will be not linear in other
Yes,
places?
if we add a lot of volume and make the drop effect very big,
Yes.
the function of gravitational forces as water volume increases might be enlarged.
Yes.
It means that the correlation might not be linear.
Then do you think your theory can show me like how volume affects the volume affects the focal length? Like can you draw a fitting line for the whole? Do you have that? Or do you think you can prove it?
Well, this is only a
Okay, it's only a part, yeah. Because I think that maybe you can consider like curvature. Like maybe you can take a picture from the side and see the curvature of the water droplet, so you can know how volume affects curvature. Then with the curvature, you can see how it will affect your focal length. I think that might be a plausible way of you solving this problem of small volume thing.
That's a valid point.
Okay, that's up.
So
give it 1 minute.
to summarize this whole the discussion, I want to say that we first talked about the lens, which I agree with the reporter when they use a camera, because if you use a phone, you cannot control when they change the focal length inside of the lens inside of the phone, which will be very hard for us to test the focal length or magnification, which will affect. And I think that for the resolution, using the formula written on the board, the S volume directly is the smallest distinguished length. So we think that if they use that to explain this theory, maybe they can do a fitting line or a fitting trend that can better explain their theory instead of putting two things that maybe not be linked together very clearly. And we think that using like testing the curvature from the side using a picture or maybe using a tracker, they can know the curvature, so the curvature can fit a better line for the larger volumes.
That's up. Reviewer, and 1 minute.
Hi, the first question. In terms of page 32. 32.
42.
32. And how would you define your magnification as compared to that?
Well, because the area is has a square correlation, and my magnification rate is defined as this.
Oh, so that's the area, not the depth, right? Okay, thanks. How do you take the medium part? 32, page 32 again. How do you just look at the middle
Because
zone?
the distortion at the edge is pretty big. It's pretty significant, and we cannot ignore that. It's up to 30%.
Okay, then can you take me through about the resolution? So how would you define the boundary that you can't tell them apart?
Well, the resolution is right here, and yes, we observe it with our eyes.
Okay, that will cause the error, right? What's your opinion?
My opinion is I think that, for example, using another app or tool, for example, I think Imager will be a good example that we can use the smaller pixel to see it from the camera's perspective, like are the pixels stay together, like the gray part together or not. I think that will be better than using human eyes.
Okay. I want to ask about the focal length. How did you define the focal length?
Well, the focal length is defined as when we have a laser beam
Right.
right here, and when the beam is the smallest, we can define it as the focal length.
How did you define what is focal length?
So we change the different focal distance in this experiment,
Right.
and we find where the point the laser beam is the smallest, and we define it as our focal difficulty.
Okay, so use your eyes, right? Okay. And what's your opinion?
I think that if, like, for example, if they use a laser light, I think like using how big the circle is, and to see when the circle is the smallest, and then we can see where the best focal is.
Okay. Then turn to Raman, your theory about the distribution.
Remaining criteria.
Right, the dance is not like this.
Sorry, time's up. You have 2 minutes to get.
can do it for us.
Okay, well, review and okay, let's start our review about the jumping microscope. We're going with the microscope and okay. We'll start with the summarize of the that's
Let me give it 1 minute.
okay.
Wait. It's okay? Connect anything?
还有很多。
你看 PFC，
再 try 一下吗？再 try 一下。这是。Okay, we continue.
Okay. Dominant effect on the glass surface and investigate the magnification and resolution of them. And this was some summary. And the ruler used the water drop on the glass surface and use a grip to control the diameter of the droplet. And move the camera or not move the camera, just move the back, move the plate to the focal length. And the parameters are the volume of the water droplet and the diameter. Okay, they measure the focal length and their series lens finger series, and they observe that when adding water, the curvature increase and the focal depth become smaller, and the resolution their series already greater, but they're not quite connected to their experiment. And the magnification is defined as the size change of the plot is observed in the camera. And distortion, they found that the distortion turned quite big when it is as the border of the document. Okay, here's some pros and cons of the revolution, and they have a great definition of the resolution and the distortion, but it helps us better know the depth. And the experimental data is quite organized and is great. But there are no error bar and no significant relation between the gradient and data, and no quantitative definition of the focal depth. This will cause an error. And the change of the ground is not quite big, so they always show a linear relation, but I think it is important. Okay. For opponents, they have a great time control and a lot of their opinions, but they didn't show some of problem. Okay. For opponents, they think the droplet is too thick. It's not the thick length to use the lens maker formula. And the reverse say, but it's right, but they compare the spherical data with the experimental data. Our view is agree, right? And they although say, did you control the focal length of the camera? Reverse answer saying yes. Our view is, though they control the focal length of the camera itself will cause some error of it. And next, for the opponent, for the solution, they need to find a better formula to fit. But before didn't done that. Our view is these formulas are all for identical lengths, and only the diffuse will tend to the solution. But in fact, it isn't an identical one. So I think it have more factors. And opponent acts on the volume influence, the focal length, and other factors, and you're going to say the chance of curvature of it.
Okay, time's up. Further, you have 2 minutes to give the conclusion remark.
Here is the concluding remarks of my report. So for the report summary, the organization will place the drop of water as a lens to investigate the focal magnification, resolution, and distortion. Our theory is the lens maker formula, the Rayleigh criterion, and the Gauss lens formula. Our clarification, we use the lens maker formula suitable for thick lens. Yes, the lens is thick because it's a sphere and not a thin. And in the small variation of water volume Vn, the volume and focal distance can be regarded as a linear relationship. And the magnification rate divided by 1 and the focal distance divided by 1 is also a linear relationship. And the intercept are close to 1. This is according to the lens maker formula. The droplet lens can have a 20 to 35% distortion at the edge, which isn't an ideal lens, which we can say that droplet isn't really ideal. The angular resolution should be revised as this formula here. Okay, for the color summary, we talked about the experimental setup, how the camera and the environmental light influence, and the washer. And experiment methodology on how the experiments are conducted. Now, how to control the droplet placement of the droplets, which we put it in the center of the washer. And the focal length of the camera, and how does it affect? Well, it doesn't, because the camera has the same focal length in the kind of washer. The resolution definition, well, we use Rayleigh criterion to compare two concepts, and we mentioned it just so that people have an idea why we assume the resolution like that. Okay, here is the discussion summary. We discussed the definition of magnification and how to increase the derivation.
Okay, time's up. Okay. So now it's our time to get a question. Any yes?
You use the laser beam to make sure the focal length, but what's the light source when you observe the image? What's the light source? What's the light?
Well, we have a light to
Which kind of light?
white light, but the laser beam has the same color, the monochromatic.
White light or real light?
Red. Mono.
But in your picture, I didn't see.
Well, I think they're actually. Here is a red laser beam in our photo. Here.
Yes, but it is conveys the focal line, the focal length. I mean, when you observe your image, what's the light source?
Well, the light source.
You use.
The light source is we use natural light. We did, yes, the environmental light. We didn't put it in black box.
Okay.
Yes.
And another stupid question: how do you make sure in your experiment the water volume in such a few water volume? How do you make sure the water volume? Okay, for example, you have 50 microliter.
Well, yes, we use the glass droplets, and it is very thin. But I think that it might be some derivation. It's a micro drop, so very thin, and of course there will be some derivation when we're using the microphone.
Magic too. Okay.
Okay. Any questions from the auditorium? Yes.
Okay, so when you take image using the camera, and then you say that you can adjust the focal length. Right? So do you use the same focal length for different image when you operate the camera? The focal length of the camera is always the same or different?
Well, the camera setting is NF setting. Yes, which means that the focal length is the same.
Focal length is the same,
Yes.
but do you think
And it can be changed by hand when we increase the camera height or something like that.
okay? So do you think the position of the image are all the same or they are different?
You mean camera?
If you use different lengths,
Yes.
different drop, and so the image of the position of the image is always the same or they are different?
I think they are mostly the same.
The same? Okay.
Yes.
How do you think?
I think as you like use different droplets because they also use different radius. So because of gravitational, like it will not like if there's few droplets, it will be more sphere. But if there's more droplets, it will not be as round on the top. It will be more flat. So we think that the focal length will be affected by this. So we think every time you change a droplet, I think the focal length should be adjusted.
And so, by controlling volume, the geographic parameters are fixed. So I think by controlling the volume of the droplets and some experience, making sure the when we control the volume, we can know the focal length. We can make sure that every time we use the same volume of water, the focal length is the same.
So probably I can follow the same question from the Professor Wu, because he mentions that you use a laser point to measure, right? So if you change the colors, like green color, green laser beam, do you make any difference? Please answer the questions. If we change the color of the laser beams,
Is it?
you change anything for his conclusion?
So is it focal length or resolution?
Anything. I just change the laser beams colors.
Yes, I think
agree.
that if you change the focal length, we think that the focal length will be shorter than red light. Like if it's blue, it will be shorter. Focal length will be shorter.
The reason is
because blue light differs because of the speed of light. Different color of speed of light in air is different.
Okay.
Yes.
how about you, Sir Liu?
It's not only the focal line,
But
focal
also-
length change, but also the magnification, the resolution.
Okay.
Right.
Okay. So Nance, what's your answer?
Because of the different reflection index and inspiration of the curvature of different colors, it will definitely affect the experimental results.
Yes, I know, but what's the result? You will be see
It
the
might
difference.
affect the focal distance,
Focal distance.
but I don't think it will affect the resolution that much.
Okay. Okay. Any question from you? No. Okay. So then we can have get a score. Okay. So we are waiting. We are get a score for the quarter. 6, 6, 7, 7, 8, and then the score for the opponent. 6, 8, 6, 8, and 8. Now the final one, the reviewer. 5, 5, 6, 6, and 7. Okay, so and these are our final stage. So